Trim and mirror mount fatigue failures represent one of the most complex durability challenges in modern automotive coatings because they occur at interfaces where multiple materials, geometries, and attachment methods converge. Unlike monolithic steel panels, these regions combine painted metal, plastic substrates, elastomers, adhesives, mechanical fasteners, and dynamic loads, all acting simultaneously over the vehicle's life. Mirror mounts and exterior trim components experience continuous vibration during driving. Wind load, road-induced vibration, and door operation generate cyclic micromovements that are transferred directly into the coating at attachment interfaces. Each cycle introduces shear and tensile stress at the coating substrate interface. Individually, these stresses are small, but cumulatively, they create fatigue damage that coatings must endure for years. Material mismatch is the primary driver of failure. Painted steel or aluminum panels expand and contract at different rates than plastic mirror housings or trim components. Temperature changes create differential movement at the interface. The coating is forced to accommodate this movement while remaining adhered to both substrate and surrounding layers. Over time, this mismatch produces interfacial strain that initiates microcracking, adhesion loss, or cohesive failure within the coating itself. Film build variation exacerbates fatigue damage. Around trim edges and mounting points, spray access is restricted, resulting in thinner films exactly where strain is highest. Surface tension effects during flow further pull material away from sharp trim boundaries. These thin regions experience higher strain per cycle, accelerating polymer fatigue and crack initiation. Adhesion chemistry is critical in these zones. Plastic trims require adhesion promoters or specialized primers to bond effectively. Any inconsistency in pretreatment, promoter coverage, or primer cure creates weak interfacial zones. Under cyclic loading, failure initiates at these weakest interfaces and propagates outward, often appearing as cracking or peeling localized around trim outlines. Fasteners and clips introduce localized stress risers. Mechanical clamping creates high compressive stress beneath fastener heads and tensile stress around their perimeters. During vibration, these stress fields fluctuate, promoting fatigue cracking in the surrounding coating. Adhesive bonded trims introduce different challenges, as adhesive shrinkage during cure adds residual stress that combines with service-induced loading. Cross-link density, again, determines fatigue resistance. Highly cross-linked clear coats resist abrasion and chemicals, but have limited elongation, making them prone to cracking under cyclic shear. More flexible systems tolerate movement, but may suffer long-term creep or dirt pickup. OEM coating systems are tuned to provide controlled flexibility at trim interfaces without compromising appearance or cleanability. Primers serve as the primary strain buffer layer. Flexible primers absorb differential movement between metal panels and plastic components, reducing stress transfer to the base coat and clear coat. Without sufficient primer compliance, fatigue damage accumulates rapidly at the decorative layers, leading to visible failure long before corrosion or structural issues arise. Additives influence performance, but within limits. Stress relief additives reduce cure-induced shrinkage, lowering initial interfacial stress. Flow and wetting additives improve coating continuity around trim edges, minimizing extreme thin spots. However, additives cannot overcome poor part design, excessive vibration, or inadequate attachment methods. Environmental exposure accelerates trim fatigue failures. UV radiation embrittles exposed polymers, reducing elongation capacity. Moisture penetration through early microcracks plasticizes the coating temporarily, followed by embrittlement during drying cycles. Dirt accumulation along trim edges increases abrasion during vibration, further degrading the coating. Detection of trim and mirror mount fatigue failures often begins with subtle visual cues. Hairline cracks following trim contours, localized gloss loss, or early delamination around mounts. Accelerated validation testing combines vibration, thermal cycling, humidity, and UV exposure to reproduce these failures before production release. From a troubleshooting standpoint, OEM engineers evaluate attachment design, material compatibility, primer flexibility, film build distribution, and cure balance. Solutions may involve increasing edge film build, modifying primer chemistry, improving adhesion promoter consistency, or redesigning trim attachments to reduce vibration amplitude. Simply repainting the affected area rarely provides durable resolution. Trim and mirror mount fatigue failures illustrate the reality of modern automotive design. Coatings must function across complex, multi-material systems subjected to continuous dynamic loading. Durability success depends on treating coatings as structural participants capable of managing strain, not just decorative layers. OEM strategies focus on compatibility, flexibility, and fatigue resistance to ensure long-term appearance and adhesion integrity. If you've observed cracking, peeling, or gloss loss concentrated around mirrors or trim outlines, leave your questions in the comments. In the next episode, we'll transition deeper into adhesion and corrosion failures driven by substrate chemistry and pretreatment variability, continuing the durability journey.